All right, we're going to be looking at a very important way of combining two or more functions in what is known as a composition. And so this is very important. We want to spend a little bit of time on this. So given two functions, f and g, the composition function, and we use a simple notation for this composition, and you'll see it right here between the f and g. It looks like a tiny little circle. Some people actually will say f circle g, f composed with g, the composition of f with g. Now some people say it's fog, and it may be a little foggy, the idea, but hopefully we'll clear it up and it won't be so foggy. But f circle g or f composed with g is the typical way of saying that. And what do we mean by that? So here's the definition of it, right? F circle g is equal to f of g of x. Now real important here, I've got f g of x. This is not f of x g of x, which is the function fg of x that we looked at in the last video. This is f of x times g of x. So real important, there's multiplication going on here in between these because you've got f of x. Is there multiplication going on between the f and the x here? No, remember this is f of x. This is really a composition if you think about it. And so here there's no multiplication here. This is not f times g of x. It wouldn't make any sense to say f times something. F is the name of the function. It's a set of instructions, right? But it's f of. So the idea here is we've got a function g, and let's just say it's a little box here, I don't know, and you know I'm plugging in, if you will, value of x into this function. I'm going to plug it in, and there's some rule, and after we determine that rule, we'll get an output. Now, what is the output? Well, the output is called g of x, right? That's the way we do it. Input x, output g of x, right? So this is not g times x. This is, you know, these parentheses are saying what we're plugging into the function. That's the input to the function x. The output is what we call g of x. Well, what we're now going to do is we're going to take this new function f, or the second function f, and we're going to take the output g of x, right, which is the dependent variable to the function g, and it's going to be the input to the function f now, the independent variable for the function f. And so what's going to come out? Well, f of what went in, g of x. And so there's the composition. So we're taking the output from one function and plugging it in as an input to another function. Okay? It's kind of a nasty proposition here if you think about it, that x is taking something in, digesting it, you know, it comes out, and then whatever comes out, well, the function f says, I'll take that. And then it operates on that and plugs an output. Okay? Well, at any rate, that's the interaction between these. Notice I can similarly define the composition g with f. Notice that's the other direction. G circle f is g of f of x. That's where we would be plugging into the function f first, right? Get f of x to come out, and then plug that into the function g. And those two directions, if you will, are not always the same. In fact, in general, they are different types of functions. Now, here's where it gets a little tricky, the domain. Let's go back to f circle g, or f composed with g. What's the domain? It's the set of all x in the domain of g. Now, why do we start with the domain of g? Because that's where we start with. You've got to be able to plug x into g to get going. It's all values of x in the domain of g, such that g of x is in the domain of f. Well, g of x is the output, and we're taking that output and plugging it into f. So it's going to have to be in the domain of f. It's got to be something that f can take in. You know, I was talking about eating things, right? So it's got to be something that f can eat, so to speak. It's kind of a gross thing, but that's what it is. So the outputs to g of x are going to be inputs to the function f, and so we need the domain to restrict any values of g of x that are not in the domain of the function f. So outputs to g must be inputs to f. Okay, so that's a little tricky, but let's take a look at it. We'll start with some simple, nice quadratic functions here, polynomial functions, and let's take a look at the compositions here. So here's my two functions, and again we'll just note that the domain of these is all real numbers. And that's good for this confusing bit right here, because we don't have to worry about it so much. Since the function f and g domain is all real numbers, it doesn't matter what comes out of f or g. The other function will be able to take whatever comes out. Anything will be in its domain, and so that's a thing we don't have to worry too much about in this particular problem as far as the domain goes. But let's look at f circle g of x. So what does that mean? F of g of x. Okay. What I like to do is simply, first of all, replace g of x with its rule. What's g of x? X squared minus 4. So keep in mind, I'm replacing g of x, right, equals to what? With its rule. I still got this f out here, so now this is what I'm plugging into the function f. This whole thing. So how does the function work, right? It's like box, right? F of box, whatever's inside here is a box, equals the box squared plus the box minus 6. So what's in the box this time? X squared minus 4. So this is going to be the box contents, which is x squared minus 4, all squared. It's very important that we put parentheses around this, right? Plus the box contents, what's inside? X squared minus 4 again. And don't forget your minus 6, okay? So I've just replaced x with x squared minus 4. Everywhere I see an x up here, I replace it with x squared minus 4. Does everyone see that? Hope so. All right, so there it is. I mean, there's the rule, but again, what we're going to often see is these things will be expanded, like terms will be combined, and then simplify if we can. And so we'll do that. Do you know how to square this quantity here? All right, I hope so. It is not x to the 4th minus 16. You just can't square this and square this. Remember, it's x squared minus 4 times x squared minus 4. You have to FOIL. First times first will be x squared times x squared, or x to the 4th. The inner and outer terms will be what? Negative 4x, negative 4x squared rather, and there'll be two of them, so negative 4x squared and negative 4x squared is negative 8x squared. And then the last is negative 4. Negative 4 times negative 4 is positive 16. So please, please, please let me know if you're having trouble with this. This is how we expand that. And this is where a lot of the algebra comes in. If you've had some trouble with it in the past, you're going to have to clean these things up. Okay. Combine like terms. Well, there's only x to the 4th, no other x to the 4th. I do have negative 8x squared plus x squared. That's negative 7x squared. And I have 16 minus 4 minus 6. 16 minus 10 is just going to give me 6. So there's f circle g of x. Composition of f with g. And so again, the domain, what was that? As we addressed all real numbers, because the domains of f and g are all real numbers. Okay. Well, let's go in the other direction then. Let's take a look at g circle f. Okay, so I'm going to replace f of x with its rule up there. Okay. And now I'm going to take this entire thing, this trinomial, I'm going to plug it into the function g. How do I do that? Everywhere I see an x, I'm going to replace it with that trinomial. So I'm going to square that trinomial and then subtract 4. That's what the rule says. Now, there it is, right? That's the answer. But again, what you might see in the back of the book is the expanded and then combining like terms form, if you will, of this expression. And so let's just do that because I think it's good. We just, in the last video, did a trinomial times a binomial. This time, squaring a trinomial times itself, or a trinomial times a trinomial. So again, remember, how do we do polynomial multiplication? Every term in this trinomial has to multiply every term in this trinomial. 3 here, 3 here. We've got 9 multiplications. X squared times x squared is x to the 4th. X squared times x is x cubed. x squared times negative 6 is negative 6x squared. So there I've multiplied everything by x squared. Now I have to multiply everything by x. X times x squared, x cubed, x times x squared, x times negative 6. And then I multiply everything by negative 6. Negative 6 times negative 6, positive 36. Whew. That's a lot of stuff to write out, so be careful, a lot to keep track of. Right. And then combine like terms. I might want to just sort of lightly cross out as I'm going here, just to keep track of things, right? What about my x cubed terms? I've got x cubed plus x cubed, that's a total of 2x cubed. I've got negative 6x squared plus 1, that's negative 5. Negative 5 minus 6 is negative 11. So I've got a total of negative 11x squared. And then the x terms, negative 6 minus 6x is negative 12x. And then 36 minus 4, 36 plus a negative 4 is 32. Whew. Okay. What's the domain of G circle F? Again, as it was with F composed with G, all real numbers. So there's our result there. And you can see clearly, notice the composition, the difference, right, in the rule, right? Really different results here. Okay? Not at all the same thing, and that's true in general. That's true in general. Okay. Now, I want to take a look at, let's go back to this F circle G function that we found. Suppose I'm interested in finding the value of F circle G of, I don't know, let's say 2. Okay, well, let's say we went through the trouble of finding this formula, so we can just plug it in. Yeah, so it's, now I can find it. 2 to the 4th minus 7 times 2 squared plus 6. And now I need to evaluate this. 2 to the 4th is 16, right? 2 times itself 4 times. 2 squared is 4. 4 times 7, that's 28. And plus 6. And so what do I get here? 16 minus 28 is negative 12. Plus 6 is negative 6, right? And there's my output. Okay, and that's certainly a valid way of doing it. Now, is there another way? Well, yeah, there is. In other words, if suppose I hadn't worked out this formula, but I did know what the original functions were. Suppose I didn't have that formula. Do I have to get the formula? Not necessarily, right? Because F circle G of 2 is what? F of G of 2. Right? But what is G of 2 equal to? Well, look at the function G of x. It's x squared minus 4. So G of 2 would be 2 squared minus 4, replacing x with 2. 2 squared is 4. 4 minus 4 is 0. Okay? So input 2 to the function G, output 0. Let me draw it. Remember that picture I was drawing up here, right, with the G and the F? Let me draw it here. What's happening? Here's G, the function. I'm inputting 2, and I'm outputting 0. And now we're going to take that 0 now, and we're going to plug it into the function f. And the question is, what do we get out of that? So I'm going to simply say this is f of what? 0. Right, so G of 2 is equal to 0. What's f of 0? Well, now I can figure that out. Here's the rule for f. And it's pretty easy to see that we get negative 6, right? That's what comes out here. Negative 6 down here. Of course, we get the same thing, right? Obviously, either way. But what I'm saying is, again, this is how to understand the way composition works. Okay, let's take a look at another example. Two more functions, and we're going to find both compositions and find their domains. So let's talk about domains for a minute here. What's the domain for the function f of x? Any problems here? Any value of x that will give us trouble? I think so. Right? If x is 0, we've got a problem. Right? So the domain here is all real numbers except 0. What about g of x? What's its domain? Do you see the problem there? What value of x will give us a problem there? And we're dividing by 0 when x is equal to what? 1, so we have to exclude that from the domain. All right, anything but 1 will work. Okay. So let's take a look at f, circle g. And what's g of x? G of x is 3 divided by x minus 1. Okay. So there's a lot going on here. 3 divided by x minus 1. That whole thing, though, is what we're going to plug into the function f. So hold on here. Function f says what? Whatever we plug in, we basically divide it into 5. We put it in the denominator, put 5 in the numerator. So this whole thing, which itself is a fraction, a rational expression, we're going to plug that in. And so let me come down here and do that. I'm going to take 5 and divide it by the input to the function, which is this whole thing here. Okay. So this is a compound fraction, right? Or compound or complex fraction. We've got little fractions out of bigger fraction. But we can clear this up, can't we? Because dividing by a fraction is the same as multiplying by what? The reciprocal. And the reciprocal of 3 divided by x minus 1 is x minus 1 divided by 3. And so a couple ways I can write this now. I can write this as 5 times x minus 1 over 3. Sure. I can also write it as 5/3 times the quantity x minus 1. I can also write it as, if I distribute 5/3 x minus 5/3. Now what type of function is that? If we were to graph this function right here, what would we get? It's going to be a line, right? It's a linear function. Slope is 5/3, y-intercept negative 5/3, right? It's a linear function. Now, say, wait a minute, linear function, domain of linear functions, all real numbers, right? I can plug any value of x in here. But not so fast. Remember how this function was created by this composition, and in that composition, we had to start with the function g. And what's the function's g's domain? Function g's domain is all real numbers except for 0, right? So we have to exclude 0. Right? We have to exclude 0. Okay. Whoop, I said that backwards. I'm sorry. That's the domain of f. The domain of g is everything except for 1. Excuse me. So we have to exclude 1, right? Because we start with that. And you can see that here clearly, right? Because this is my input, 3 divided by x minus 1. So we know, when we look at the domain, we know that x cannot equal 1 since we start with g of x. Okay. But also, what has to be true? We're taking g of x and plugging it into the function f of x. Okay, now this is where, so g of x, what? Its output cannot be what? Cannot be 0. That's the domain of the function f of x. Since I'm plugging the output to g of x into the function f of x, right, then g of x, we know, cannot be 0. So the question, is there any value of x? Such that g of x equals 0? Is there any such value of x? Is there any such value of x? Well, think about it. G of x again is what? 3 divided by x minus 1. Can that ever equal 0? Can I ever divide 3 by anything and get 0? Somebody says, oh yeah, if x is 1, that'll work. Really? If x is 1, I've got 3 divided by 0. 3 divided by 0 is undefined. 3 divided by 0 is not equal to 0. Okay? So is there any way to get 0 when you divide into 3? Answer, no. The only way we get an output of 0 is if I divide into 0 by a non-zero number. Okay? And so the bottom line is we can say the domain of F circle G is all real numbers except for 1. We don't have any problem. Once we get the output to the function G, its output will be guaranteed never to equal 0. It's guaranteed never to equal 0 because I can never get an output, or we could call that what the range of the function G is never 0. The range of the function G. Okay. What about the other direction? Let's look at the other direction. So this was F circle G of X. And here's the, any one of these would be fine for the rule for F circle G of X, technically. And if you think about the graph of the function, it's a line, except there's a hole at x equal 1. At x equal 1, there's a hole. Okay. Going in the other direction, we have this. Right? F of x was 5 divided by x. Okay. And what was g of x again? All the way to the top. Remember, g of x is 3 divided by x minus 1. So I'm replacing x here in this with 5 divided by x. Okay. There's my answer. Again, though, this is a compound fraction, except this is not one fraction. I can combine it as one pretty easily. But I'm going to clean this up a little bit quicker. If you remember my technique I've used before, I'm going to multiply by 1 in the form of the least common denominator of all my smaller fractions. Right. Well, this denominator is x. 1 is 1 divided by 1. 3 is 3 divided by 1. So the LCD is just x of all the little fractions. And this will give me what? X times 3 is 3x. Here I distribute x times 5 divided by x is just 5. 1 times x is x. So I can simplify in that form. So this is the rule. Okay. And so what's our domain now? What's our domain? So the domain, we start with the function f. What was the domain of the function f? What could we not plug into the function f? Remember, all real numbers except for 0, right? So we have to exclude 0, right? So x cannot be equal to 0. But also the output to f of x, right? That's going into the function g of x, and its domain was everything except for 1, right? I can't plug in 1 because I would be dividing by 0. So f of x cannot be equal to 1. And if I look at f of x, which was 3 divided by x minus 1, sorry, I said that wrong. F of x is 5 divided by x. That cannot be equal to 1. What value, is there any value of x that will make 5 divided by x equal to 1? Yeah, x equal 5. So notice x cannot equal 5 either. Now, notice in the final simplified result that I have here, we can tell that, can you not? 5 minus x, right? Clearly x cannot be 5 or I'd be dividing by 0. Okay, but again, be careful because in the simplified results, as we saw in the previous example, sometimes that we can lose that information. In the last video, sorry, we saw an example of that. Okay, but this tells me together, right, that the domain is all real numbers except for 0 and 5. And 5 we can see, but notice in this simplified form, 0, you could plug a 0 in, right? 3 times 0 is 0, 5 minus 0 is 5, 0 divided by 5 is 0. But again, we can't plug in 0 because remember where we started with. We started with the function f of x. Okay. So it's a little tricky with the domain when you're talking about compositions of functions. Again, you can see the different compositions. F circle G, right, gave us this formula here, which is a linear function, right, except there was a hole in it. And then G circle F function is this, which is a rational function, which has a vertical asymptote if you think about, right, we were analyzing rational functions a while back, and so clearly I think you can see we have a vertical asymptote when x is equal to 5 here. Okay, but different results nonetheless. Okay, one more example. What's the domain of this function? X plus 4 has to be what? Greater than or equal to 0. So x is greater than or equal to negative 4. Okay, so in interval notation we're talking about this as the domain of that function. G of x, what's its domain? It's just a polynomial function, a quadratic function, so its domain is all real numbers, no problem. Okay. So let's take a look at F circle G. So what is the function g of x? It's x squared minus 4. So I'm going to plug that into, remember this is not multiplication, it's not f times this, it's f of this. So everywhere I see an x, I'm going to add 4 to it and then take the square root. And so what am I replacing x with? X squared minus 4. So there's x, add 4 to this, and then take the square root. So this is all x, and I've done that. Now take a look at this. This simplifies very quickly, right? Negative 4 plus 4 is indeed 0, and I'm left with the square root of x squared. And somebody says, hey, that looks like we can simplify that. I know the square root of x squared is equal to what? Well, you might have forgot this, but the square root of x squared is actually equal to the absolute value of x. Say, what? Well, it's just x. All right. This is something that we talk about, you should have talked about it in your elementary algebra when you were dealing with radicals and exponents and such. Right. A misconception is to say that x squared, take the square root, is always equal to x. Well, that's not true for all real numbers. In particular, it's not true if x is any negative number. Like if I plug in x is negative 3, right, over here x is negative 3, right? So I would get, negative 3 on this side. Here I square negative 3, what do I get? Squaring a negative gives me what? Positive, right? Positive 9. And the square root of 9 is what? Positive 3. Are these two numbers equal to each other? No, they're not equal, right? This is not true. This is only true if x is equal to a non-negative number. How do we make this statement true for positive and negatives? Answer, we do the absolute value, right? Because now what's the absolute value of negative 3? What's that equal to? 3. Now they're both equal. Okay, so that's a misconception, and sometimes when we're teaching this subject we talk about this, but then when we're saying simplifying expressions we'll say, oh, just assume the variable x is always positive, and then you don't have to worry about the absolute value bars. But in this case we do, because again, we haven't made any restrictions on x yet, but I guess let's talk about the domain now. Because I mean, if you just look at this, say, I could take the absolute value of anything, right? So this tells me the domain's all real numbers. But remember what we have here. We started with the function g of x. What's its domain? All real numbers, right? But g of x, right, what we're getting out of g of x is going into the function f of x, and it has a domain restriction, right? Has to be greater than or equal to negative 4. So g of x must be greater than or equal to negative 4. Well, what is g of x? G of x is x squared minus 4. Okay, well, look at that inequality. Right? This is not a linear inequality, it's a polynomial inequality, which we talked about previously. What do I want to do here? Get 0 over here, right? Well, I can add 4 to both sides, and I get x squared is greater than or equal to 0. Well, wait a minute, let's think about this. X squared greater than or equal to 0. Think about that. X squared greater than or equal to 0. You even know what the graph of x squared looks like. For any value of x, x squared is greater than or equal to 0. Right? Whenever you square a number, it's always non-negative. And so this is true for all real numbers, right? And therefore, the domain is also all real numbers. So the composition function comes out to be the absolute value of x. Domain all real numbers. Very interesting that we composed two functions like this to get the absolute value function. Let's look at it from the other direction. Let's look at G circle F, and then we'll end this video, and then we'll look at one more after this one. So f of x, again, what was that function? The square root of x plus 4. Okay, and now we're going to plug this into the function g. So what's the function g say? Well, it's right here, x squared minus 4. So whatever I plug in, I'm going to square it and subtract 4. So what am I plugging in? This whole radical expression. So the square root of x plus 4, I'm going to plug that in. I'm going to replace it with x, I'm going to square it, and I'm going to subtract 4 from that result. Well, now, when I have the square root of something and then I square it, right, that certainly is just going to cancel out the square root, right? This is to the 1/2 power, right? X plus 4 to the 1/2 power. 1/2 times 2 is 1. I just get x plus 4 to the first power, or x plus 4. Minus 4, well, that becomes simply x, right? Plus 4 minus 4. Hey, that's interesting. Not the absolute value of x this time, but I get x. Okay, but what's the domain here? Well, remember, we started with the function f of x, right? What's its domain? Right? Its domain was what? Everything greater than or equal to -4. Right? And we can see that, right? I have to have the value under the radical must be non-negative. And then, well, of course, we're plugging the output to f of x into g of x. But remember, g of x domain's all real numbers, so there's no problem there. We can plug anything we want in there. But this restriction says our domain is everything greater than or equal to -4. So what's the graph of this function look like? So this is the function g circle f of x is equal to x. And what's the graph of this function look like? Well, we know what the function f of x equals x. It's a line of slope 1 passing through the origin. So what would this graph look like? Well, here's -4. The domain is -4 to infinity, so we start at -4 at an output, input -4, output -4, right? Because the graph is input x, output x, right? G circle f of x is equal to x, right? And so we get this line of slope 1 passing through the origin, except it's a half line, if you will, or a ray. It starts from this point here on. That's the graph of our function. Okay, so there's certainly lots more ways we can combine functions of different types, and so you're going to be doing that in the homework and working on that. And so, but this gives you hopefully a little guidance about how we do function composition. Again, a very important operation with functions.